Okay, so today is the third day of this course. This outline I had given to you earlier, we have done up to this point. And then the remaining 3 days, I suppose I'll try to cover most of the other stuff that are listed there. First of all, are there any questions about the material that was discussed in the last two lectures?
That equals to average over sigma I square average. That can you just mathematically show that, or is it a definition?
No, I mean, this is what we did. One of the things that we did last time. Now, the fact that, for example, just let me then onto this. Here. This is something that I had worked it out. No, I mean, when alpha is not equal to beta, then each replica index will give you one thermal average.
But H effective is not exactly, H effective has no JIJ, right? But I remember you started with a Hamiltonian which had JIJs explicitly sitting.
Yeah. So, I mean, that comes from the fact that, what is the effective Hamiltonian? The effective Hamiltonian was the replicated Hamiltonian. Again, go back one step. So, basically this is the replicated Hamiltonian. At this point, there is Jij, and when I take this average outside, then this Jij go away. But the effective Hamiltonian is defined in terms of that. So instead of doing the Jij average here, I could say that I will do the Jij average later on, after I do the sigma trace. See.
Okay.
So that gets interchanged basically. I mean, when we're doing that, with respect to H effective, but that is equivalent to doing it also here. Instead of going to effective, I will do the averaging here. And then here you have a sum over replicas. So if I have, let's say, sigma I alpha, then the alpha replica will go with the corresponding term in the Hamiltonian. If I have sigma I beta, then the beta term will go with the corresponding term in the Hamiltonian. And each of them will give you an average for that particular Jijs. Right? So if I had some, let's say, sigma I alpha, sigma j alpha, then only the alpha, here there is a sum over alpha. So when the alpha here matches the alpha that I have put outside, only that comes into the picture. The others will be basically, when you do the trace, others will be just a free trace, which will give you the partition function. Right? So for if I have any number of terms here, some of them come with replica index alpha, some of them come with replica index beta, which is beta is not different, not the same as alpha, and etc. etc. For each replica index, you have to pull out the term which carries that replica index, and then do the average. And for if there are many different terms, some of them have different replica indices, then for each of these replica indices, you get a thermal average. And you get a product of the thermal averages. And then at the end, you do this average over the Jijs. So eventually, one is doing the calculation with this. But if I want to look at averages, I can look at it with respect to this effective Hamiltonian or that, because these two are equivalent to each other. Okay, so any other question? Anybody else? Okay, so then we'll proceed. We'll proceed with the Sherrington-Kirkpatrick model, where we've done part of the work. Basically, it's an infinite range model, and every spin sigma I interacts with every other spin sigma j. Coupling constants are independent random variables. which at this point we are taking a simple distribution. We are taking this average value to be equal to 0. So there is no possibility of a ferromagnetic or anti-ferromagnetic ordering. But taking some kind of a Gaussian average, Gaussian distribution, and J squared average, you have to scale it by n to make sure that you eventually get the thermodynamic limit properly, in the sense that the internal energy, etc., will be proportional to the number of spins. So, and that is required. I mean, this kind of scaling is required for that. Then, you can do this average, replicate, and then do the average. And then this is basically the problem, that have the different replicas are coupled. There is no disorder in the problem anymore, and you have to basically take a trace over all the replicated spin variables. And to work this out, one can make use of this Hubbard-Stefanovic transformation, because this whole thing can be written as a square. And if you do that, then for each pair alpha beta, each pair of replica indices alpha and beta, you introduce these auxiliary variables, q alpha beta, and then you are doing basically a Gaussian integral. So there is a q squared thing in the exponential, and the other thing basically becomes linear in this q alpha beta, and also in this in the previous slide, what you have here is sigma I alpha, sigma I beta, and then sigma j. So I don't know, breaking it up into two different things. One over sum over I, and the other is sum over j. For every pair, there will be a auxiliary variable coming from this Hubbard transformation, and then this is, there is just a couple of lines of algebra, which is very simple. You don't have to really, I don't have to really work it out on the board. What you get is basically something which gives you a free energy per spin. Little f is the total free energy divided by the number of spins that you have in the system. Beta is 1 over kBt. And then this becomes a function of this q alpha betas. After, one is eventually, of course, have to do the trace. So this quantity L involves this exponential L. You have to take this trace, take the log to put it back into the exponent. And so basically this whole thing comes with sits in the exponent, and then it comes with basically a factor of n, and we are taking the n going to infinity limit. So that's a saddle point method. We have to basically take the minimum of this quantity with respect to all these q alpha betas. So up to this point, there is no approximation, except that we have done this calculation using the replica method. So eventually here we'll treat this n as some integer, but eventually you have to take this n going to 0 limit, which causes some discomfort. But that's what people did at that point, and people have found out that that way of doing things is okay. So for this admittedly artificial model where we have infinite range interactions, the mathematical problem then becomes just this: that you have this quantities q alpha beta, which can have value from minus infinity to plus infinity. And this is symmetric, so alpha beta and beta alpha, you don't have to distinguish between them. But alpha and beta each can take n values, because that's how we have done. Number of replicas is equal to n. So there are n times n minus 1 divided by 2 quantities here, q alpha beta. And we have here a function of this q alpha beta. This part of the function is quite simple, but the other part is not quite simple, because you have this q alpha beta here, and then you have this sigma alpha, sigma beta. You have to take a trace over that, and then take the log, etc., etc. But you end up eventually with, again, another function of this q alpha beta, set of parameters q alpha beta. And the procedure that you have to adopt eventually is to find a minimum of this quantity with respect to this q alpha betas. And if you find a minimum, then basically the values of q alpha beta in that minimum will tell you about what is going on in the system, because that will give you the free energy, and from that you can calculate many other quantities that you are interested in. right? So, but at this point, we don't know anything about these Q alpha betas. So when these people, Sherrington and Kirkpatrick, first wrote down this model and did their calculation, they made the simplest approximation, that this Q alpha beta does not depend on which alpha and which beta you are talking about. It's the same for every pair. As long as alpha is not equal to beta, then it has the same value. And that assumption is called the replica symmetric approximation, because then you say that all the replicas are equivalent. Don't make any distinction between which alpha and which beta you are considering, but as long as they are not the same, you will have this answers. So nobody tells me at that point that the true minimum of that function is actually replica symmetric, but that's the simplest approximation, and so one proceeded with that for not alpha not equal to beta, and then the calculation becomes very simple, because you see here this Q alpha beta, if you say that it doesn't depend on which alpha and which beta you are talking about, then it's just that you can take outside, and you have a sigma alpha, sigma beta, sum over alpha and beta. So again, that becomes basically the square of sum over alpha, sigma alpha whole squared. Again, you can introduce one more auxiliary variable through this Gaussian approximation, Gaussian transformation, and then one can calculate the trace. This is basically what I had asked you to do for the infinite range ferromagnetic model. There was no alpha and beta, but there was I and j. So basically, you had sigma I, sigma j, sum over I and j in that case, and then you could convert that into a square of something and use etc. etc. So the same procedure now can be applied to solve this problem, which I will not work out explicitly, but this is basically you have this Gaussian variable minus z squared over 2, and when you take the trace, you get this hyperbolic tangent. I mean, when you have sigma variables, Ising variables, and you take trace with respect to that, then typically you get a hyperbolic tangent. So basically, then if I now do that, then this quantity is then determined in terms of the only one parameter, which is this Q. I have assumed that Q alpha beta is equal to Q when alpha is not equal to beta. Only one parameter. So then your free energy becomes a function of that Q, and you minimize your free energy with respect to that Q, and that gives you the standard mean field kind of self-consistency condition for this order parameter Q. And again, of course, as you can see here, you have to then find a non-zero Q solution. And to do that, I mean, we can say that it's a continuous transition. So this quantity near the transition, this Q is small, and then you do the expansion of this hyperbolic tangent in a power series, and you will get something. The first term will of course go to 0 because it is a z here, and when you integrate with respect to z, then that will give you 0. Second one will give you z squared multiplied by q, and that will give you something which is non-zero, which is actually unity because you're doing an integration with z squared over 2. So when on the right hand side, the first term will be proportional to q. There will be higher order terms, etc. There will be fourth order terms and things like that. So this is the standard kind of Landau kind of expansion that you have. When you have Landau theory, which has let's say m squared term and m to the fourth term, etc., etc. There again, you have an expansion. If you minimize that, you will get a linear term, and then we'll get a cubic term, and so on and so forth. And the TC is determined by when the coefficient of the q term on the right hand side matches the coefficient on this side. So that you can see here that q will be non-zero for t less than tc, and this is just this beta j that come in here. So
how this q alpha beta equal to q is an assumption?
Yeah. At this point, it is assumption of replica symmetry.
But does it follow by minimizing that free energy?
So that question will be asked, yes. That is the subsequent development. So if one gets a solution which under this assumption, and that solution has physical properties. And if one can show, second thing is that if one can show that that is actually a minimum, in the sense that, in the expanded space where you allow all the Q alpha betas to vary with alpha and beta, in that space where this replica symmetry answer give you a minimum at least.
Okay. No, the alpha beta independence is fine, but the equality is equal to that order parameter. Q is order parameter. So
Yeah, yeah.
how did that become equal to order parameter? That's the
So that you have to basically go back previous state. So Q at this point, this Q are these parameters that you have introduced by doing this Gaussian transformation. So now when you know the order parameter is Q alpha, sigma beta average, right? This is the kind of order parameter that we are dealing with. So you calculate now, after having done all of that, you calculate sigma I alpha, sigma I beta average. And that will be this Q. Just like, when you do this calculation for the infinite range ferromagnetic model, then you introduce this again Gaussian, through this Gaussian transformation, introduce a parameter which is sort of like this exponential minus x squared over 2, and x couples to sum over I sigma I. At that point, this x is just a parameter. But I mean, you can calculate sigma I average using that. And then one would see that, that sigma I, the order parameter that you are interested in, that is actually the value of that quantity at the minimum. Yeah.
So no, this is what is J naught here. It's a different, another parameter.
It is another model, yeah.
No? Oh, this is a different model.
So, I mean, you can also sort of, this sort of makes some sort of heuristic sense, which says that, you see, I mean, in the main field theory, you say that there is a local field acting on that particle, and then that gives you the magnetization and so on, and you get a hyperbolic tangent function. Here you're saying that the local field itself has this Z, which is itself a random variable. So very roughly speaking, I mean, what we are saying is that the local field that a particle is seeing coming from its interaction with other particles itself is a random variable which has this kind of Gaussian statistics. And because of this Gaussian statistics, if we just had a hyperbolic tangent, if we had just one power of the magnetization, that would average out to 0. So then you have to, if you take the square of that, in the definition of this Q, we have sigma I average squared. That is basically giving you this hyperbolic tangent squared. And then you average over the probability distribution of that local field that a particular spin is seeing. And so, I mean, at this point, then from here, I assume all of you realize that this will have a non-zero solution when t is less than tc, and tc is just this related to the variance of this random interactions that a spin has with all the other spins. So, of course, here there is only one. The distribution is characterized by this only j. The average value is equal to 0. But you could also, of course, I mean, carry out the same calculations. Now with Pjij, instead of this being centered at 0, you say that Jij minus some J0 squared, where the average value will be non-zero. And that J0 you have to scale by n. Again, infinite range model, there is the ferromagnetic model, your coupling constant had to be scaled by n to get the thermodynamic limit, right? So if you do that, and this is something that I'll again leave it to you as an exercise. This whole thing can be carried out, and it's a very simple thing to do. I mean, because that other term that we'll get, I mean, what will you get? You will get Jij times sigma I alpha sigma j alpha in the replicated language, and then you have to shift basically that when you do the integration. There will be a J0 term, which will just couple to sigma I alpha, sigma j alpha, sigma I alpha. So in addition to that, in addition to all the terms, in addition to these terms that we have, there will be a term which will be related to J0 times sigma I alpha sigma J alpha. So you just carry through and you will basically find the same kind of situation. Of course, I mean, now we'll have a free energy function that that will have both. I mean, here you have this J, but there will be also some J0 term which comes with the magnetization. And then there will be two different kinds of order parameter. Because now if you have a situation where the distribution of Jij actually has a non-zero average value, then there is a possibility of having some kind of a ferromagnetic phase. Of course, I mean, if you have non-zero average and then you have a broad distribution about that average value, then there is a competition between which phase will be the appropriate one, which phase gives you lower free energy. And that calculation can be done in exactly the same way. And then you have these two parameters. One is, well, T over J, temperature, just made it non-dimensional. And similarly, J0 over J, J0 being the average value of the distribution of the interaction strength. And what we have done here till now is basically this line, where this J0 is equal to 0. And then there is at T equals J, there is a transition from a spin glass to a paramagnet. And this line gets extended, but if J0 is sufficiently large, then the spin glass phase is not there. Instead, you have a ferromagnetic phase. And again, there is a paramagnetic to ferromagnetic transition. This phase diagram also has this funny thing that, this is at 1, but this is at 1.25. So if you're coming down slightly above 1, then there could be some kind of a reentrant spin glass phase. Initially, you will go into some ferromagnetic phase, but then at lower temperatures, it will go into some kind of a spin glass phase. So this is, in some sense, if you, as long as you are willing to accept this replica symmetric ansatz, this is basically the solution of that model. One more thing that one can do is, in addition to just these interactions, Jij interactions, one can also put in some kind of a magnetic field. So then, we have three parameters. One is the average value of the interaction. The other is this J, which is the spread of the interaction. And then, of course, there is also a magnetic field. And when we have a magnetic field, then again, we'll have non-zero magnetization and things like that. So again, one can deal with it in the same framework. I will not do that explicitly. All you have to do is to here include a term which is minus H times sum over I, sigma I. And I'm not saying that this random field, I mean, people have also looked at random field models, but here we are not doing that. We are looking at a uniform field. And again, just go through this procedure and you will have an expression for the free energy in terms of now it will involve a term which has this magnetic field sitting there. No, it's not exactly the same, but the equations are similar. So, I mean, it will be something like that, yes. Yeah, because I mean, when you decouple that, then you will get something which is linear, and the field also will be linear. So I mean, it will be basically here. Here we will have a magnetic field term. Yeah. Huh? Characteristics are, you see this P, paramagnetic phase is where M is equal to 0, Q is equal to 0. This is the high temperature phase. Ferromagnetic phase where M is not equal to 0, and when M is not equal to 0, automatically Q is not equal to 0. Whereas here, M is equal to 0 and Q is not equal to 0. So, I mean, this field thing I'll come, this is one of the things that we want to talk about later. For the time being, let's just look at this when the field is equal to 0, and also when this J0 is equal to 0. As I said, extensions to those cases, non-zero average value and external field, one should be able to work it out using this framework that I have just discussed when these things are set equal to 0. So fine, so this is a paper, this is a Physics of Letters paper, which created a lot of interest because here is an exact solution, so to speak, of a model, although this model is not a physical model because it has infinite range interactions. But still, it's a mathematical problem and a conceptual problem in the sense that it shows that it is possible to have a transition where you go from non-zero value of zero value of Q to a non-zero value of Q at some temperature. But then, when people sort of looked at this solution in more detail, there were some issues, very serious issues, in the sense that, once you know this, I mean, if you accept this, then you can calculate any thermodynamic quantity that you want, right? I mean, here, once you have found the value of Q, then you go back here, evaluate this quantity, and as a function of temperature, for example. And you can do it above TC. Above TC, there is no problem. Below TC, people found out that it gives you unphysical results, such as negative entropy. When you have the free energy, then you take derivatives with this temperature, it will give you entropy. Of course, I mean, there you have to put in the temperature dependence of this Q, etc., etc. But that, you do that all the time, right? I mean, when you do mean field theory for the Ising model, again, below the transition, there is an order parameter, which is non-zero, and you evaluate the free energy for that non-zero value of the order parameter. And that gives you a function of temperature, and then from that you calculate heat capacity, entropy, internal energy, all these things you can calculate. The question is, I mean, for this problem, if you do that, then whether you get some physical results or unphysical results. And people soon found out that this solution, which is mathematically a simple thing to study, gives you unphysical properties for all t less than this Tc. It's not that, just near the transition, it still has physical properties. And then as you go to lower temperatures, something else happens and the properties become unphysical. It is not like that. What one finds is that as soon as Q is non-zero, according to that solution, then you will end up with consequences which are not physical. So this negative entropy is something that, I mean, all of you realize that, why it cannot be negative, right? I mean, in this case. Yeah, so I mean, that's the usual definition. But I mean, here, since we are dealing with discrete spins, you can sort of count the number of configurations. But if you had continuous spins, then sometimes, classical models may give you negative entropy. Have you seen things like that? I mean, if you have, for example, Heisenberg model where you have classical spins and which are continuous variables, the angles are continuous variables. There, how do you count number of configurations? There is some difficulty there, and people say that you have to look at low temperatures, very low temperatures. There is a problem, and you have to look at basically the quantum version, because at low temperatures, classical statistics is no longer a good one. But anyway, so I mean, this is something that people have thought about many, many years ago. And for Ising model, there is no reason why one could end up with a situation like that, because here it's a discrete model. So for each energy, you can find out, for example, how many configurations are there, which are characteristic of that particular energy. And so there is no room for negative entropy in this case. And so, although this solution looked like a nice way of describing the spin glass physics, this solution is not the correct solution. And then people try to figure out, where does it go wrong? Why it is not the correct solution? And there, these people, Thouless in particular, David Thouless, and he had a student, De Almeida, they sort of pointed out what is wrong with this solution. And again, this is something which is very general. So I do want to spend a little bit of time on what is being done here. So this is true for any sort of situation where you have a function of many variables and you want to find the minimum of that function. So
proceed, can I ask one question? Like what happens to dependence of Q on temperature for T less than J?
That you can calculate from this equation. That again, I'll just leave you with an exercise. Just to do an expansion of these things in powers of Q. So there will be here we'll get a linear term, and then we'll get again higher order term, Q squared term. And then you find out, I mean, the T is TC. So the linear term will have a coefficient, I mean, if you bring it to the other side, 1 minus T by TC.
But these experimental curves that you were showing yesterday, like, how well does it compare with those things?
There, I don't think, just this equation, first of all, I know for T less than TC, of course, I mean, this whole thing doesn't work. But this will show some change in slope. But I don't think it will show, something which is very similar to what you see in experiments. I mean, because of the fact that, here we are dealing with a very artificial model and things like that. And this is mean field theory. So, I mean, this is a general thing that you're looking at some phase transition. And let's say, again, simplifying model phase transition. There you can do mean field theory. Mean field theory will give you something that, you have the Landau function, whereas first term is m squared, second term is m to the fourth, etc., etc. You minimize that. For T less than TC, it will give you a non-zero m. But it will be proportional to, again, you will find that m is proportional to square root of T minus TC. But in experiments, real experiments, you don't find that. Because that's mean field theory, and the mean field theory results, although they are in some sense qualitatively correct, they are not quantitatively correct, in the sense that the values of the exponents that you get from mean field theory are not the values that you will find in real experiments. So same thing here. Here you will find that the exponent is 1 instead of square root. Q is proportional to T minus TC. But again, that's a mean field theory, and one doesn't expect to see those exponents in reality. And this equation itself is not valid, as we'll see as we go along, that where you have assumed replica symmetry, those equations do not describe the ordered state correctly. So this is again, I have done this equation, there is no issue. This equation is something that you have just done by some algebraic manipulations. You have done the n going to 0 limit, you have done the Gaussian approximation, and then you have done the saddle point. So there is a function of this so many variables, and that gives you f, and you are supposed to find a minimum of this f. And it's a function of many variables. So I mean, this issue will come up again later on. I mean, many of the other kind of areas. For example, if you are doing optimization problem and things like traveling salesman problem and stuff like that, where you have basically a lot of degrees of freedom, and you want to find out a minimum in the space of those degrees of freedom. So there, the standard method is that you have to first find a stationary solution, which is the first derivatives of whatever quantity you are trying to minimize. First derivative of that quantity with respect to each of the arguments have to be equal to 0. And that is basically fine. I mean, you can what we have done till now, I mean, the replica symmetric is, there is a manifold I am looking at where all these Q alpha betas are assumed to be same. And within that manifold, I'm trying to find what is the value of Q that will minimize. And minimize basically again means the first derivative will be equal to 0. You can calculate second derivatives and check it whether it's a minimum or a maximum or whatever. But that is a very restricted way of minimizing this function, because the function itself has so many variables. I mean, the basic problem here is, of course, I mean, if you look at this Q alpha beta, as I said, there are n times n minus 1 divided by 2. In principle, so many quantities. Eventually, we let n go to 0. So, I mean, this becomes all somewhat little, difficult to digest. But I mean, let's say we are looking at something which is n is like 10 or some such thing like that, some positive integer for which there's no difficulty in dealing with something that looks like this. And there, I can find a stationary solution in a particular manifold. But the question is, of course, the fluctuations can take you outside that manifold. So we are assuming that all the Q alpha betas are the same as Q0, and then trying to find the value of Q0, which minimizes the function. But then to decide whether that is an appropriate solution, you have to look at whether it's actually a minimum in the full space of the Q alpha betas. So then this is the procedure. No? I mean, when you let's say, I mean, the standard thing is actually again a particle system where you have interactions among the particles, and you want to find out what is the ground state. Then you again look at the function, which is a function of the positions of all the particles, and you try to minimize that. And to minimize that, again, you first look at the first derivative, and then if you find a solution, then you look at the second derivative. So what is the second derivative? That first derivative is equal to 0. Second derivative is what we call the Hessian matrix. It's a function of many variables. So you look at, let's say, variables are x1 up to xn, then you look at second derivative, del squared, that function, del xi, del xj. And that gives you basically a matrix, and you basically have to look at the eigenvalues of those matrices, that matrix, and make sure that the eigenvalues are positive. There's something that all of you know, right? I mean, that's so this is basically what one is trying to do here in this context. So here the variables are Q alpha beta, symmetric. So alpha beta, beta alpha, one doesn't have to distinguish. But we are looking at in the Sherrington-Kirkpatrick solution, we are looking at replica symmetric solution where this Q alpha beta equals Q0. If I want to look at the stability of that solution, if I want to find out whether it actually corresponds to a minimum or not, then I have to allow fluctuations which take you outside this replica symmetric manifold and arbitrary delta Q alpha beta.
This the first term, like for when you assume this Q alpha beta is Q basically, so for all the first terms, can I just do a simple listing, right? N into n minus 1 by 2 Q square, and then that one is just 1 plus Q square. Basically.
Yeah, it's just.
So only the second term gives some non-trivial.
Slightly, yeah, right.
Okay.
Second term gives you this hyperbolic tangent squared integrated over this auxiliary variable.
So if I take some finite n and compute the eigenvalues of the Hessian, let's say, so there I can see that it actually becomes unstable. Is that right? Like for a finite
n, it probably will. I mean, that depends on which n you are taking. So on instability that people saw was in the n going to 0 limit.
But how can I do that? I mean, okay, like I can't do it numerically, right?
No, you cannot do it numerically. This will have to be done analytically. And this Thoules, Almeida and Thoules, they actually wrote down this Hessian matrix.
Okay, so there's no way one can check this ideas numerically.
You can check these ideas, but I mean, what problem would that correspond to? I mean, for arbitrary value of n. So you have.
So I can only do integer n.
You can do integer n, means that basically means that n different Ising models which are coupled to each other.
Right. Yeah. No, I'm just talking about this question of stability of the Hessian thing.
Okay.
So that also I can do it for any finite, like integer n.
Integer n, you should be able to.
And from those results, I can't really say anything about what happens in this particular limit, right?
I don't think so, in the sense that
I can't extrapolate or
extrapolate to n going to 0. That's, I mean, one can certainly do that. I mean, I don't know whether that has been done. I have not seen that being done. But one thing that one would find if you do that, then you'll see that there will be some eigenvalue which will have some dependence on n. And whether that dependence, when you extrapolate to n going to 0, whether that agrees with what these people got using the n going to 0, that I don't know. Okay, so this is what is being done here. So I mean, basically, what one is doing is that this solution was obtained by Sherrington and Kirkpatrick, and then one is looking at deviations from that solution, and one is not restricting these deviations to have any particular dependence on alpha and beta. And so then the first derivative, of course, is 0. That is, we are expanding about some stationary point. So then we'll have beta fq0, and then you have the second derivative matrix, and then delta q alpha beta, delta q gamma delta. Now, this matrix itself has, of course, 2 indices, but each index is actually a pair index. So alpha beta, that can have n times n minus 1 over 2 different values, and similarly gamma delta also have n times n minus 1 over 2 different values. So the dimensionality of this matrix, Hessian matrix, is n times n minus 1 over 2 in one direction and also in the other direction. So one has to construct this matrix. And if you are very much interested in how that is done, I mean, we had, I have some write-up here, which is basically how to write down the different elements of this matrix and then take the n going to 0 limit and then trying to figure out. So it's not just the writing down of the matrix. Eventually, we'll have to find the eigenvalues of this matrix. We have to diagonalize that matrix. And it is not so difficult because you see, what you have here is this quadratic term. So I mean, basically what you have to do is take 2 derivatives of this free energy, one with respect to q alpha beta and the other with respect to q gamma delta. There is a quadratic term, so that's sort of give you the diagonal term. And then there will be other terms here. And this L is what? See, L has this q alpha beta times sigma alpha sigma beta. So when you take a derivative with respect to q alpha beta, then you bring out sigma alpha sigma beta average. Take one more derivative, then you will have 4 sigmas. And the 4 sigmas will have their alpha beta gamma delta indices. And depending on whether this alpha beta and gamma delta, whether they are equal or whether one is equal to the other, I mean, there are various possibilities. And each of these possibilities you have to look at. And those possibilities you will be able to relate to this quantity, to something that looks like this. Not always this hyperbolic tangent squared, but some of the cases you will see hyperbolic tangent to the 4th and so on and so forth. So writing down the elements of this matrix is a little tedious because then you have to take 2 derivatives and then you have 4 indices, then you have to see how these first 2 indices, second 2 indices to what extent they match, etc., etc. But once you do that, then all the elements of this matrix can be obtained. And if anybody is interested, then I can sort of write down a few of these elements later on when we do the tutorial. So then one would construct this matrix, and then from the symmetries that you have in that matrix, then one can also find the eigenvalues. So then that is what this calculation is all about, that one has a replica symmetric solution, and then one is looking at fluctuations about that replica symmetric solution. And that will tell you about whether the solution that I'm looking at is a stable solution or not. And people found that for all temperatures less than this characteristic temperature, the critical temperature for transition, this condition is not satisfied. So that is basically the instability of the replica symmetric solution. The symmetric solution that Sherrington and Kirkpatrick wrote down, which is sort of the simplest solution that one can think of. Unfortunately, that solution does not describe the physics in the spin glass phase. In the paramagnetic phase, there is no issue. But as soon as you go into the spin glass phase, then one finds that one eigenvalue of this Hessian matrix that becomes negative. And as a result, and this is the reason why people found this unphysical behavior. People found this negative entropy and things like that in the low temperature phase of the replica symmetric solution. So then, some understanding is there that tells you about why the solution that Sherrington and Kirkpatrick obtained, why that is not the correct solution. And this is the work of these people, Almeida and Thouless. And again, it's not just for this model, it's for the model where they have put in and also external magnetic field, which couples to the sigmas. So then what I am talking about is when this field is equal to 0. And here, of course, this T by J equal to 1 is the transition point. So above this temperature, the system is in the paramagnetic phase. And one finds that as soon as you go to a temperature which is lower, then one enters into this spin glass phase. And there, the replica symmetric solution is no longer the correct one. If you include a magnetic field, then this point becomes a continuous line. And again, one can calculate this line exactly. And one finds that this sort of asymptotically approaches 0. But if you have some sort of some amount of magnetic field, which is somewhere around here, then as we are reducing temperature, there would still be a transition. And this transition will be marked by the breaking of replica symmetry. So when you have a magnetic field, then of course your Q is always non-zero. When you have a magnetic field, then your magnetization is always non-zero. So you cannot treat that as, in some sense, a order parameter. Then what you have to look at is basically whether one is getting into a phase which is different from the high temperature phase. And that difference will be signaled by the breaking of replica symmetry. And what is the meaning of breaking of replica symmetry? That's, of course, we have to understand later on. And that basically, we'll see, corresponds to a transition from some kind of a simple phase to a complex phase. In the sense that simple phase will be one in which you don't have very long time scales, you don't have very complicated free energy landscape and things like that. Whereas in the spin glass phase, necessarily, you will have a very complicated landscape, and that will lead to very slow dynamics and things like that. So the SK model, one is predicting that even in the presence of a magnetic field, this is important, because even in the presence of a magnetic field, there can be a transition, and this transition will be signaled by the breaking of replica symmetry. Here we have found out that already is true. And similarly, if I repeat the calculation with some non-zero value of h, again, one would find that there will be a point temperature at which replica symmetry will be broken. Now, what happens beyond that, this calculation doesn't tell me. So what is the solution for t less than 1 when h is equal to 0? This, the calculation of Thouless and Almeida, they don't tell me anything about that. Similarly, what happens here? Same sort of a question arises. Replica symmetry is broken, but then what is the right solution? Yes.
So does replica symmetry breaking means like for replica symmetry, all the replicas have same Q, the order parameter is same. Does in this breaking phase and replica symmetry breaking, all the replicas can have different order parameter values?
Yeah. So, Q alpha beta is equal to Q for all pair alpha and beta. That's the symmetric solution. So anything that goes beyond that, is that your Q alpha beta will depend on which alpha and which beta you are talking about.
So
It will not be the same for every pair alpha beta.
So in that case, like there is no particular order parameter for the system.
We'll see. I mean, this is what Parisi got the Nobel Prize for. Specifically, there will be an order parameter, at least for this model, that's exact. The order parameter will not be just a number.
Okay.
Order parameter itself will be a function defined on the unit interval. And when that function is uniformly equal to 0, that you have the paramagnetic phase. But as soon as you get into the spin glass phase, this function has a non-trivial dependence on the unit interval.
What will it depend on? Kind of means it looks like it depends on alpha beta.
Yeah, so I mean, that's what we'll go into that. The way that replica symmetry is to be broken is something that people didn't know. I mean, so various things were tried. Eventually, Parisi came up with a scheme which seems to work. So that is where this escape model discussions will end. I mean, what is the right solution? Which alpha and which beta you are talking about? Yes. So I mean, this is the standard. I mean, broken symmetry notion is not any different from the standard broken symmetry definition. That if you have, for example, a ferromagnet, there it's a three-dimensional spin. So you have x and y and z components. And Hamiltonian is invariant under that. I mean, which you call x, which you call y and z, it doesn't matter. But as you go into the ordered phase, that rotational symmetry is broken. So then if it orders along the z direction, that direction becomes different from the x and y directions. And that is happening spontaneously. It's not that you may apply a field in the z direction or something like that. So here also, I mean, instead of having just one index, there you have a vector, so you have basically one index, the component index, whether you are looking at the x component, y component, and z component. But here you are looking at a quantity which has two levels, alpha and beta. The question is whether the specific alpha and specific beta that you are looking at, whether the value of that quantity does depend on that or not. I mean, whether it's the same for all pairs alpha beta, or there are some special values or some special choices of this alpha and beta.
SK is the ferromagnetic part and Parisi is the spin.
No. SK is just, yeah, there might be a little confusion. Anything which is not paramagnetic is the Parisi part, basically, in the sense that here we are not talking about, of course, J0. One can extend that picture also to J0. So here one is in the paramagnetic part, then SK works. But as soon as you, I mean, just as we had found out here, as soon as you cross this line, let's say J0 is equal to 0, as soon as you cross this line, replica symmetry is broken. And then you need Parisi. You cannot do SK anymore. There also, if I remember correctly, there is replica symmetry is broken here also. As soon as there is this strong disorder in some sense, and there is a large value of J. But that I'll come back to you about that in the next tomorrow, because I am not 100% sure I remember it correctly, that whether anything that is not paramagnetic is where replica symmetry is broken. But in that Almeida-Thouless line, we are not talking about this J0 being non-zero. We're just looking at this line, but then there is an external magnetic field. So this is the transition that we have been talking about, when the field is equal to 0 and you are changing temperature. And there, replica symmetry is broken at this point. And anything below, everywhere below, it is Parisi in the sense that difference between SK and Parisi is where replica symmetry is broken or not. SK is the paramagnetic, SK is the symmetric solution, replica symmetric solution, and Parisi is a solution where the replica symmetry is broken. And as here, I mean, J0 is equal to 0, that's what he's saying. But then when you apply a magnetic field, then this point where the replica symmetry is broken, that itself changes. And it remains, there is a finite value of temperature at which replica symmetry is broken, even when you have external magnetic field. And that sort of leads me to guess that here also replica symmetry will be broken. Because I mean, when you have a magnetic field, of course, your magnetization is non-zero. But then there's a difference between the replica symmetric phase and the replica symmetry broken phase, even in the presence of a magnetic field. And this is actually something which is very controversial, in the sense that later on, I mean, when we talk about whether this kind of phase diagram is applicable to short-range systems or not, there many people claim that as soon as we apply a magnetic field, there cannot be any phase transition anymore. There is no unmated Thouless line. Whereas, you know, this kind of replica symmetry breaking transition will predict that even in the presence of a magnetic field, there can be a transition from a high temperature sort of trivial phase to a low temperature complex phase. Okay, so this is the instability. This is what we have done until now, that we found out that the SK solution is not a physical solution at low temperatures. And the reason that it is not, doesn't give you physical results is that it is unstable in the extended space.
For the, I mean, so we had the phase diagram with J0 and T, and now it's H and T. So can you go to the next? Yeah. So this H and T. So this Almeida Thouless line is also the line I would just get from the mean field solution, right? That is
to the replica symmetric.
From the replica symmetry. It's exactly that.
Yeah.
And
so, I mean, you know, there will be now a third axis. I mean, you can assume.
If J0,
J0,
but otherwise it's on the J0 equal to 0 plane. This is the phase diagram. Okay.
And the thing that I don't remember very well is that now if you take this third reaction and make J0 large, then there would be a ferromagnetic phase. And
but is Q 0 in that SK phase?
Q will not be 0 in the SK phase as long as there is a magnetic field.
Okay, only for H0 it's
only for H equals 0. So that is the subtlety, no? I mean, when you have a magnetic field, that will always produce some kind of a magnetization. It will break the up-down symmetry. So Q will be non-zero at any temperature. So even in that presence of that symmetry breaking, up-down symmetry breaking, whether you can still have this kind of a phase transition. Okay, so then that brings me to the, in some sense, to the end of discussions of, well, I mean, there are still many things to discuss. So, so up to this point now, we have found out that let's again, you know, not so much worry about H. I mean, just to understand the physics, I mean, one can look at the H equals 0 line, that above this temperature, you have a paramagnet, and then below this, you have something else. You don't have the replica symmetric solution in the sense that that is not the right solution, but you have something happening. And the clearest indication of what is happening is this replica symmetry breaking. But what does it mean? I mean, so that is the thing that people, first of all, you know, when you say that that symmetry is broken, there are infinitely many ways of breaking that symmetry. You say that Q alpha beta now depends on which alpha and which beta you are considering. But you know, it doesn't tell you how to choose, in some sense, the Q alpha betas when that symmetry is broken. So various people tried various things. And this is where Parisi came into the picture. He actually didn't do any work on spin glasses before he wrote this paper. So it's pretty much, you know, this first work on spin glasses. And somehow, you know, he came up with the correct solution. And people were talking about things like, you know, one-step replica symmetry breaking, for example, is where this alpha beta, the dependence on this alpha and beta can be thought of in a simple way. I mean, you just look at blocks and things like that. That is what we'll be doing. So what is the problem? So the problem is basically that you have this Q alpha beta, which is basically alpha goes from 1 to n, beta goes from 1 to n. So there are n squared elements. N squared elements are all of them are not interesting because diagonal elements are essentially something which doesn't matter. I mean, only alpha not equal to beta are the quantities that are of interest. So we can set the diagonal elements equal to 0, and this matrix is symmetric. So you have this n times n minus 1 over 2 independent quantities. And these quantities now will all not be the same. The replica symmetric ansatz is where all these off-diagonal elements have the same value. Right? Now you say that all of them cannot have the same value. But nobody tells you a priori how to assign these values. So people tried various things. And one thing that even Parisi, his first paper was on that, basically, where you do one-step replica symmetry breaking. And the way that that is done is what I have expressed here. So this is a n by n matrix. And now you say that you have these blocks. Okay, each block is M1 by M1. So let's say M0 is, I call it M0. M0 is n, the original dimension. I mean, to appreciate that, this you have to sort of think in terms of a situation where this n is like a large positive number. So it's, let's say, if it is like 100 by 100 matrix, but then you can always break it up earlier in the symmetric answers. All the off-diagonal elements of this 100 by 100 matrix are the same value. But now we say that I'll do one-step replica symmetry breaking. What does it mean? That I will draw these blocks which are M1 by M1. And M1 is something that, of course, has to be less than n. And if you are doing it right for a real integer and so on and so forth, M1 has to be, one has to be able to divide basically M0 by M1 with some integer quantity. In other words, M0 has to be equal to an integer multiple of this M1. And so you have this M1 by M1 matrices. And then there are these diagonal blocks. And then there are these off-diagonal blocks. So you say that these off-diagonal blocks, all elements on these off-diagonal blocks will have some value of Q. And all off-diagonal elements in this block will have a different value of Q. Right? So, I mean, if you want to draw this matrix, then it will be somewhat like this. So this is your and here you are doing this blocking. And this will continue. And this is, let's say, this direction. This is beta and this is alpha. All the diagonal elements don't worry about. But here, the off-diagonal elements, so I mean, I just draw the diagonal elements. Here, the off-diagonal elements will have some, let's say, Q0. And all this space will be Q1. Here also, all the diagonal elements will be Q0. And here also will Q1, like that. So I have broken up my matrix into this smaller blocks. And within each block, I have one value of Q. And outside the block, we have a different value of Q. And this whole thing is is equal dimension n, and this dimension in this picture I call that this n is m0 original, and this is m1. Within each of these diagonal blocks, there is no difference between this and this and that. But there again, you know, diagonal elements I don't care about. I put them equal to 0, but all the off-diagonal elements I'll put equal to some number, Q0. And then all the off-diagonal elements which are not sitting inside these diagonal blocks, then I'll put them equal to Q1. And so now there are two parameters. One is this M1, and well, three parameters. So M1 is there, and then they choose this Q0 and this Q1. Okay, so yes. Yes. So what that means is something that, of course, one has to worry about. At this point, it is just a mathematical exercise that you are trying to parameterize a n by n matrix, and there are infinitely many ways of doing that. So depending on your intuition or whatever, you try out various things, and this is one of the things that was tried out.
Chandan, I'm from the notation that you used there. It looks like Q0 should be outside.
Q of M0. You can say, well, I mean,
M0 was like Q0, right?
Yeah. M0 is equal to n. So, right. So, I mean, you know, what he has done is in this picture, it's done iteratively. So, let's say I just stop at level 1. So, there will be two such. See, I mean, here, what is done is this itself is now written in terms of, is also done the, this itself doesn't, is not parameterized just by one number. So you have two numbers here. I mean, if I just stop here, then this M1 by M1 block will be something that will not have this substructure anymore.
So if you stop there, then
what happens here? I mean, it has not.
QM1, right? Or
yeah, you can call it QM1. Yeah. So I mean, you know, that I call Q0 and the other one I call Q1. So I mean, in this picture, yeah, sure. I mean, you know, you'd like to call this. If you say that this outside thing is Q of M0. And then this will be Q of M1. All of these are Q of M0. So the point is now there are these two things that we have done. We have chosen this M0. M0 is not chosen. M0 is equal to n, but we have chosen this M1 of this size of these blocks. And then I'm saying that within these blocks, the off-diagonal elements has some number, which is called Q of M1. And outside this blocks, the off-diagonal elements will have some other value, Q of M0. So this is the way that symmetry has been broken in one step. And now the problem is, again, not so difficult to look at. You basically have to go back and calculate this quantity. Now you know that you have parameterized this Q alpha beta in a particular way, which involves this this M1. And now instead of having just one Q, which is you have these two Qs corresponding to this and that. So again, you will have a function which involves these three parameters, and then you minimize that free energy with respect to these three parameters to find out how these things depend on temperature and things like that. So that calculation also, I mean, I have some notes where that calculation is done. So if anybody wants to look at that, we can share that.
The three parameters means Q0, Q1, and M3 also. Is it? M1.
M1. Yeah. M0 is n, but this whole thing, of course, in this picture is not so difficult to figure out. But then eventually you have to let this n go to 0. So then how to look at it is not something that is very clear. Okay. So this actually is also important. This is called one RSB, one step replica symmetry breaking. And there are models where actually this one RSB solution turns out to be the right solution. That you, of course, I mean, you have to eventually find what this M1 and this QM0 and QM1, these things are, by doing the calculation, by looking at that free energy, appropriate free energy, and minimizing it with respect to these parameters. So, I mean, there are some systems where one can just stop at this one RSB. And at that point, I mean, when this Sherrington-Kirkpatrick model was being done, people didn't know about these other models. So later on, people came up with these other models where this one-step RSB gives you the right solution. But unfortunately, what people found is that if I stop at this level, the sort of pathologies that you have in the SK model, replica symmetric solution, they are not cured completely. In the sense that one still has all these issues that the quantities which should be positive, like the entropy, etc., they're at low enough temperatures, they become negative and so on and so forth.
But is it that you can go a bit into, and then it's fine?
Yeah.
Okay.
I'm sorry, say that again?
You can go into the line a bit,
yeah.
Then it's okay.
Then it's okay. So it is not broken at exactly the same temperature as for the fully replica symmetric solution, but so then, what the Parisi did was to sort of continue this kind of blocking in an iterative way. Okay, you can the picture, from the picture, it is not so difficult to see. I mean, what we have done is, first of all, the original matrix I have broken up into this blocks, but each of these blocks, which is M1 by M1 block, I can again break up into M2 by M2 diagonal blocks, and then that will, I mean, this QM1 or this block, which is now M1 in this direction and M1 in that direction, I can again, do this, and this will be now M2. And I will say that, the inside this block and outside this block is different now. Earlier, for each of this block, I had just Q of M1. So here I will have a Q of M2 in addition to Q of M1. And then, one can continue this sort of ad infinitum. And then you end up with all these things. Sizes of the blocks and the Qs that you associate with this off-diagonal elements in these individual blocks. Okay, is that construction?
Is this iterative procedure, like, does it converge, like once you find that this pathology is cleared at some case step, then all remaining steps it will be clear?
That people have not done. People have, I think, as far as I remember, one RSB was done and its stability, etc., were looked at, or it's got two-step RSB is again something was done, but then Parisi went to infinite step RSB in between.
In between this.
And if you have 50-step RSB, nobody has done the calculation. So this is the bottom line, so to speak, that this solution was then constructed iteratively by saying that you have these parameters, Q of M0, Q of M1, etc. Just like we have done here, Q of M0 and then Q of M1. Here you will have Q of M2, all those things. So these are now parameters that you are using to basically write down this matrix Q alpha beta. not just these parameters, but also these sizes, M1, M2 up to the sizes of these subblocks. And for some value of k, then you have to basically write. Is there any physical motivation for this kind of construction for replicas? Yeah, we'll come to that. I mean, at this point, it is no physical motivation. It is just a mathematical exercise, and Parisi thought that this is a nice way of doing things, so maybe this will work. But the physical interpretation of this is something that we have to look at, and that is in the agenda. So when you go to this k going to infinity limit, then basically you will have these values M1, M2 up to Mk can be represented by continuous variable, and by choosing, it's normalization, so to speak. You can say that that goes from 0 to 1, and the corresponding q then becomes a continuous function. So that is basically the next step, that you do these iterations infinitely many times. This k you make go to infinity, and these m's then are defined as each of these m's correspond to some point in the unit interval going from 0 to 1, and this is what I have written down: k going to infinity. Then this m's are represented by continuous variable, and this q of mi corresponds to then a function of this x. So this I'm not going to today. So this is then at this point it is just a mathematical procedure, that a particular way of breaking replica symmetry was considered by doing this blocking, and then we apply that infinitely many times, do this iteratively infinitely many times. That then leads to a description where you have this continuous variable that tells you about the different values of these m's, and then you have a function of that continuous variable that tells you about the q's that you associate with the different levels of this blocking. So then you have a qx order parameter function, and you basically then write the free energy. Yeah, so yes, sure. Yes. So all these m's are supposed to be basically, these are factors, integer factors of n. So you start with the simplest way of doing that is some 2 to the 10. You start with the second one is then 2 to the 9, etc., etc. But that you can do for large positive integers. But what here something is cutting off for some reason. But anyway, so that is not important. So what I'm getting at is then you have a q of x, which is how this q depends on this m, which is now replaced by a continuous variable. And then your free energy becomes a functional of this q of x. I hope you understand that, because now you see, now it's going in the other direction. Yeah. So this was my expression for the free energy, and it was written in terms of this q alpha betas. And the q alpha betas then I have parameterized in terms of this function q of x, where x goes from 0 to 1. So somehow we have to write this sums and what you get when you do this trace, etc., in terms of this function. And then you have to minimize that quantity, that functional, with respect to this q of x, to find what is the q of x that is appropriate for particular temperature and things like that. So that is there in the Parisi paper.
definition of Q had summation Q alpha.
Definition of the order parameter.
Yeah, Q is the order parameter.
Order parameter was just Q alpha, Q beta.
Was not summation.
Well, now we have broken replica symmetry. So then you have to put in the summation.
Okay, if it is summation, then that expression you have.
Yeah. Then that is, this basically comes from that.
The integral, right?
Yeah.
So, but, there is a degeneracy in a sense that the outermost, let's say Q0s are way more in quantity than Q1, and then Q1 are in lesser quantity than, and more quantity than Q2. So there should be some additional factor.
That depends on how you define this interval and how you define the function. So I mean, you can include that in the definition of what you call this Q of X. Yeah. So yeah, so that is the next point, that now we have this. So I mean, what I'm saying is that now you have a functional of this function Q of X, and you have to minimize that to find out what is the Q of X which is appropriate. And typically, I mean, that's not a very easy thing to do. It cannot be done at arbitrary temperatures, but for temperatures close to the transition temperature, where you can do an expansion in powers of Q. In other words, I mean, it's a continuous transition. So all the Qs are small, close to that transition temperature, just below the transition temperature, where you can actually carry this thing out explicitly. And one finds that slightly below the critical temperature, one finds that this Q of X as a function of X has this particular form. So it is again characterized by these two quantities. One is X1 and the other is this Q max. And one can calculate both this X1 and Q max in terms of temperatures and things like that. Now, the next question that would appear then would come up is that now we have a Q of X, and you see that Q of X has a dependence on X. So how do you relate your physical quantities to this Q of X? So again, that is something that there was a lot of controversy about that. What people eventually found out is that now, see, earlier your Q equilibrium order parameter, the Edwards-Anderson order parameter, was this Q, which was just sigma alpha, sigma beta. This was done earlier. And one is saying that this didn't depend on what alpha and what beta one is looking at. But that's a replica symmetric ansatz. But now things do depend on alpha and beta. So now you have to define it by something that looks like this, sum over. And then you have to divide it by. And if you do that, this sum over alpha not equal to beta basically involves this integral over this variable x. And so you get the equilibrium. This is the definition of the equilibrium Edwards-Anderson order parameter that you get as an integral of this Q of X over all of X. So all these things can be done explicitly near the TC, where everything is small. So one can do the standard sort of Landau expansion kind of thing, where you expand in terms of these order parameters, which will be small, just below the critical temperature, and various characteristics of how this Q equilibrium, how that depends on temperature, etc., etc. All these things can be calculated. So I have not gone through how one goes to the k going to infinity limit explicitly from these quantities, etc., etc. Which again, this is certainly a little technical, but at least for the one-step RSB, how to write down the free energy and how to basically find out the corresponding parameters. This one-step RSB, of course, there is this M1 and this two values of Q that are the parameters. Those things one can do fairly easily. But then, extending that scheme to infinitely many such subdivisions, is a little difficult, but again, it's not such a difficult thing as long as you accept what is being done. I mean, so accepting what is being done is not so easy in the sense that it involves taking limits which seem sort of unphysical. But it turns out that at least for the SK models, this is the right solution, in the sense that people now, of course, one has to now look at, I mean, earlier the Sherrington-Kirkpatrick solution was rejected because it was unstable. So now one has to show that this is not unstable. So that people have done. It turns out that it is sort of marginal, that there are some zero eigenvalues, but there are no negative eigenvalues when you look at fluctuations about this solution. And what is more is that there are subsequently, much later after this was done, there was some sort of rigorous mathematical treatment, which I don't understand at all, which is not published in any paper, but there's a book that one has written, and this guy called Talagrand, who has a book which shows that in a rigorous mathematical sense, the results that you get from this way of breaking the Replica symmetry is the right way of doing things.
Before this, in the SK one, you had this like Q equal to that integral then 10 hyperbolic squared, isn't it? So now when you have this Q, this functional Q as a function of X, so do you have a similar relation? Can one write down, or that's not possible? Like Qx equal to something which involves some Qy and then.
So what does this Q of X mean is still not clear from here, right?
And one doesn't have a self-consistent equation like the one you had before.
Oh, so the Q of X itself will be determined by some kind of a self-consistent equation similar.
But is it like a simple?
Having a number,
yeah,
you have a self-consistent equation for this function.
But like Qx might involve Qy also or something like that.
Integral equation, it will be
Integral
some kind of an integral equation.
And that equation is simple, or?
That equation becomes simple near TC, where you can do this expansion and things like that.
Okay.
But much lower than TC, it's not simple. I mean, so it's not so easy to find out what is the self-consistent form of this.
Even the form is not okay.
Hello. So here we want to just put this Qx and that free energy, and then we optimize that free energy.
Yes.
And find the optimal Qx.
Right.
So this is kind of a functional optimization.
Yeah.
Is this a standard procedure?
No, I mean, I don't know of any other phase transition, for example, where the order parameter is not just a number, it's a function.
Yeah.
So if it's just a number, then of course it becomes a function of that number, and you just find the value of that number which minimizes that function. But this kind of optimization with respect to a function that is actually there in many StatMech problems.
Okay.
For example, I mean, you look at, I mean, this is a standard problem where it appears is that you have some Ginzburg-Landau theory, right? Ginzburg-Landau theory is written in terms of an order parameter function now. In the Ginzburg-Landau, it's not the Landau expansion, but it's a full theory. It's a field theory now, in where you write the free energy as a functional of the order parameter function. And then you say that I want to find out, for example, I have some boundary conditions. On this side, I say that the order parameter should be positive. On that side, the order parameter should be negative. Whatever, I mean, some kind of strange boundary conditions. And you want to find out how this field behaves. Now the field is not uniform. I mean, if you have simple boundary conditions, then the minimum of that functional will be where the field is the same everywhere. But now, let's say if you have some boundary condition which says that on the surface the field is fixed by some experiments or something like that, and you want to find out how the field behaves inside. There it's a functional minimization, that you have a functional and you have to find out the function which minimizes that functional. It is not unheard of, but I mean, in the context of Landau theory, usually, I mean, you have a free energy written in terms of an order parameter, which is a number. But here, the order parameter itself is a function.
Sir, How did you from this two summation get one integral 0 to 1?
So this, you have to do basically the actual way in which the sigma alpha, sigma beta is represented in terms of this Q of X. And as far as I can tell, this way of doing things, again, I'm not sure, you have to check it yourself, that if I do a sum over beta, then does it depend on alpha or not? So this Q alpha beta, I'm keeping this index constant. I'm just summing over all the other indices. Huh? Sorry, what did you say? So, I mean, the actual definition that I wrote down is the one that you sum over both alpha and beta. But this way of breaking replica symmetry, as far as I can remember, if I keep one of the labels a constant, but the other one I'm summing over all possible values, then it doesn't depend on which alpha you are using. So if that happens, then you sum over both alpha and beta and then do 1 over n minus 1. It's going to give you the same thing.
So, Chandan, I mean, so initially both MI and QMIs were variational parameters, right?
Mm-hmm.
So, but then somehow the MI got converted to a continuous variable in X, and only Q of X was the kind of variational.
Mm-hmm.
So why is that? I mean, like, why does why
So
did MI just get promoted to kind of a...
So, I mean, what I suppose, again, something that remains to be seen. So this is my interval, and this is my M1 or whatever. Yeah, M1 was block size, yeah. So, I mean, this M0 is bigger than M1, right? And so this is M0. So, yeah, so exactly how then one converts this to X is something that I am not 100% sure. Let me see. So essentially, I mean, one is doing things like this. These are the sort of things that will appear. That Qj is associated with one of these off-diagonal things, and then Mj minus Mj. This you have some matrix Mj times Mj matrix, and then you are breaking up into Mj plus 1, Mj plus 1 matrices. So I mean here, if you do that, then this QM0 will appear M0 minus M1 times. Basically, when you do this kind of things, when you sum over all the labels. So this is basically what one is doing over there. You are taking one label constant and then summing over all the other labels. So this kind of a thing will become this, and this is with, typically you want to write that as qx dx. This is some interval in the 0, 1, and then there is a number associated with that. So all of these things, of course, will become dense as you go to larger and larger values of levels of replica symmetry breaking.
And is there any reason to think of this kind of a structure? Like, I mean, like this is not something one would naturally think of, right? Like,
not that I know of. I mean, eventually we'll see that there are lots of nice structures that come in. I mean, there's this ultrametricity and things like that. That also comes from this solution. So kind of tree-like structure seems to be the right thing for this model, at least. Whether that remains valid for short-range models and things like that, that is not clear.
okay, so I guess we'll stop here, right?
Yeah, I guess, yeah.
So I think today you'll take the tutorial, right?
You can take
At
but
6.
It's the first slot or second slot?
First slot, right? 6.